Hey friends, welcome to our channel. Let's have a look at a newly appeared problem, Zero Array Transformation 2. In this video, our plan is to address this problem by two very classic methods. So the algorithms involved, let me first write this. One is a line sweep algorithm, and the other one is binary search. So if you are not very familiar with these two algorithms, you're welcome to check some textbook or see some Wikipedia pages to get yourself familiar with those two algorithms. So here we basically have an array, and also we have a 2D array called queries, which give you a index range and a value of its upper bound, which you can decrement the value. So here the main thing is that this value is an upper bound. You can decrement and 0, 1 is up to this value I if value is greater than 1. See, so the amount by which each value is decremented can be chosen independently for each index. So this is the very core, right? One is this is the upper bound. The other is that within this range, so as long as your decrement is bounded above by this value, you can decrement whatever amount based on each index, right? So we want to make this array 0, means all the elements to be 0, using as less queries as possible, right? So here we want to return the minimum possible non-negative value of key, such that after the first key queries in sequence, this number becomes 0. If no such key exists, return -1. So actually, if you look at the two examples, they give very detailed explanation. In particular, example 2, you cannot make it 0 using the queries given here, right? So the constraints are the following. So the length of this nums can be as long as 10 to the power 5. Also the query, right? So this means that we need to take into consideration of time complexity, right? So with that said, we are ready to explain the algorithm. So here, actually, if we were to use the first key queries, so we need to get how much amount we can decrement at most for a certain index, right? So here, let's say first step. For each index, so we need to get the upper bound of decrement, right? Given the first key query. So if this upper bound, total upper bound, let's see, the upper bound, let's call this bound, let's see, B, right? If for each index corresponding to a value, so let's see I, so this is BI, let's see. If your number, so nums at index I, is less than or equal to this overall bound for this number, then you can make this index value, the value at this index, you can make this index element to be 0, right? If we can make for all the indices, we can make the whole array 0. So this is exactly this can be exactly treated by line sweep algorithm, right? So this is step 1. Step 2. So find the minimum key such that we can zero out the array as the rule or the requirement of the current problem, right? So for sure we cannot test by key, each key, right? So here we are going to do binary search, right? So here the binary search, the 2 steps. One is that you define a Boolean function to yield order, and then you do search space shrinkage, right? So this will be our overall plan and all steps. So with that said, I guess still you might have some problems here. So now let me walk you through example 1. So here, as we already know that we can use key equals 2, but let me get all those, right? So here, let me first, here the length of this nums is 3, right? So let's first make a array of index, say, length 4, right? Mean I add 1 base here because I'm going to use one more index. So from index 0 to 2, you can at most decrement by 1. So let's first add this to this 0 to 2, right? So 0 to 2, you can have 1, 1, and 1. So this is the most you can do. And then the second query is 0 to 2, you can do 1, right? So this is the first, and then for the second one, you can do decrement by another 1. So you have 2, 2, 2 overall. And for the third one, you can do for index 1, you can decrement by 3. So that is overall is 5, right? So then you check at which step you are able to have a bound. You can decrement is greater than or equal to the numbers. So if you look at this, so at step 0, because you have 2 here, for example, 2 is greater than 1. So for using k equals 1, you cannot do this. And then when k equals 2, right, you can do this because all the decrement amount is greater than or equal to the corresponding values here, right? For sure, if you use k equals 3, you can do it. But here is the right one, the minimal one. But how do we get this list effectively, right? If you look at the procedure, you should already realize this is nothing but line swipe algorithm, right? So when we do this, of course, we are not going to do a k equals 1, k equals 2 like here we walk through, but we are going to use binary search. So for the second part, we are going to explain it during the coding. So now let's move to the coding part. So first, I'm going to get the n, there's the length of this nums. Also, I can get the length of this queries, right? So now let me first make some preparation. So let's define this part, define the Boolean function, right? So define the Boolean function, so can finish. So in other words, if I use key queries, if I can finish and make it the original nums array 0. So this way, we first need to get this list and using key operations. So this can be done like this. So we can do d equals, this is a list. So here I'm using n plus 1, because this way we have n plus 1 index. You will see why, because we are using line swipe. So then for I in range key. So here in order to make it, I'm going to use key and the minimum of m, right? Because we have at most m queries, right? So in this case, we can first get the value and the bound, that is queries I, right? So once we enter this bound, so we're going to increment, we can decrement this value by value at most. In order to get the overall statistics, let's do this. dl is incremented by dl. Then once we exit this bound, so we are going to decrement, right? So this is the main algorithm. So then what we do, actually, in order to get the cumulative effect, so we are going to do for I in range, say 1, n plus 1. So here we have r plus 1. That's why here I'm using n plus 1, right? So then what we do is dr and di is incremented by di plus minus 1. So this is the cumulative sum, right? So then what we want to do, so you can print out this d just for visualization, but what we want to return is that nums I is less than or equal to di for I in range n. If this hold, then we can zero out the original array using those key queries. So here, let me annotate that. If we can zero out the nums array using key queries, first key queries. Right. So let me make a call for example 1, because the example 1 we can finish, right? So print can finish. Let's use 2, right? Because 2 it should return true. Yeah, you can return true. This is 2220 exactly here. So now if I call 3, for sure it will also finish, right? Any number greater than or equal to 2 you can finish. Then the query, the resulted this is 2520, corresponding to this one, right? So now we finish this part. So this function we write can finish from here, this line up to here. So this is the so-called line swipe algorithm. So this we use line swipe algorithm to write a Boolean function for our binary search here. So once we have this, so then actually let me comment out this print, because we don't need that anymore. So what we do actually is binary search, right? So in order to do this, let me first check transform this problem into a binary search problem, and then we do some edge case. So here we want to find the mean key such that can finish key is true, right? So an edge case is like this. If we use all the queries we cannot finish, then we should return -1. So if can finish m, right? So if we cannot finish, so we should return -1. Otherwise, so we can design the search space and then do shrinkage, right? So here we write low and high. So low can be as low as 0, right? If it's originally just all zeros. And also we can write m or m plus 1. So here why we can write m plus 1 is due to the way we write the can finish function. But here if we write m, it's still okay. So then we are doing this while low is less than high. So we can get the midpoint from low to walk halfway. So low minus high, integer division by 2. So if can finish mid, in other words, this mid still makes this true. So we can even make it the overall result smaller. So we can set high equals mid. Otherwise, if at midpoint we cannot finish, so we need to use more queries. So we are going to set mid equals not low equals mid plus 1. So overall, we can return this low, right? So this will form the full actually code for this problem. Let me first submit that and then make several comments. Yeah, it passes the 2 test cases. So now let's look at the generic case. Yeah, it passes all the cases. As I already have walked through example 1 and print out some of the Ds, you should have a clear understanding at this point. So now let me comment on this problem. So you know our strategy is to decompose the solution into 2 parts. So one is a line sweep algorithm and the other is a binary search, right? So actually there are a number of problems in LeetCode for which you can solve using line sweep. You're welcome to practice those problems. And another technique is binary search. So here we are using binary search in a more dedicated way. So we first define a Boolean function to yield order. So this order actually determines also how you find the search space, like here, and how you do search space shrinkage, like here, right? You do the shrinkage. So that's basically a very classic but very powerful technique. So actually in our video, in our channel, we have a playlist on binary search. You're always welcome to practice the problems using that playlist. Hopefully it will give you a lot of information and insights. So with that said, I guess that's basically about it for the current video. Thank you for watching.